Hello everyone, I am Dr. VRAO. In the last class, that is in the lecture 36, we had gone through the terminology of electrochemistry. That is, we had gone through the what is meant by electric conductor, conductance, types of conductors, conductance, specific conductance, equivalent conductance, and molar conductance. And also we had gone through the effect of dilution on specific conductance. Okay, so we had gone through the effect of dilution on conductance and effect of dilution on specific conductance. Okay, so now in this class we shall see effect of dilution on equivalent conductance, right? And to know about before we are going to study the effect of dilution on equivalent conductance, we should know another terminology, that is conductance ratio. We should know the term conductance ratio. Conductance ratio. Conductance ratio is being represented by alpha, and that alpha is equal to equivalent conductance at any concentration by equivalent conductance at infinite dilution, right? So conductance ratio, it is the ratio of equivalent conductance at any concentration to the equivalent conductance at infinite dilution, right? So in order to understand conductance ratio, we should know what is lambda c and what is lambda infinite. This word, this letter is called as actually that is we know the small letter lambda. Okay, in Greek this is capital lambda, this is a small lambda, this is capital lambda, right? So lambda c by lambda infinite. Okay, so lambda c is equivalent conductance, equivalent conductance at any concentration, right? And lambda infinite is equal to equivalent conductance at infinite dilution, okay. First of all, you should know the difference between equivalent conductance at any concentration and equivalent conductance at infinite dilution. So let me explain the difference between equivalent conductance at particular difference between these two. Okay, so for that you take let us take 10 liters container. Let us take 10 liters container, right? So let us take 10 liters container. This is the container of 10 liters, okay, in which we shall take let us take 5.8 grams of sodium chloride, in which this is the 10 liter container in which we shall take 5.8 grams of sodium chloride. So to this let us add 1 liter water. Okay, to add 1 liter water. So what happens, 1 liter water in which 5.8 grams of sodium chloride is dissolved in 1 liter water. Its concentration is, we know the molarity is equal to, or normality or molarity both are same for sodium chloride. Okay, weight by gram molecular weight into 1 by V in liters or 1000 by V in ml. Okay, so weight is 5.8 by 58 into 1 by 1, that is 0.1. So its concentration is 0.1 molar or 0.1 normal. So let us measure the equivalent conductance. So equivalent conductance at this concentration is represented as lambda C. So lambda C, where concentration is 0.1, where concentration is 0.1. So at this 0.1 molar concentration, if we measure the conductance, if we measure the equivalent conductance, that equivalent conductance is known as equivalent conductance at a particular concentration of or concentration of 0.1, right. Now, so if we add one more liter, we do not add extra amount of sodium chloride to this solution, we just let us add one more liter water, that is the total volume is 2 liters. The total volume is 2 liters. For example, at a total volume of 1 liter, equivalent conductance is for example, let us say that the equivalent conductance is found to be or comes out to be. For example, if we suppose if the equivalent conductance of this solution is comes out to be 1 gram equivalent inverse 1 gram equivalent inverse centimeter square. Okay, that is 1 gram equivalent inverse centimeter square. Okay, we know that okay. So if we found that 1 ohm inverse, units for equivalent conductance is ohm inverse centimeter square gram equivalent inverse. That is the conductance at total volume of 1 liter, and if we add one more liter, that is total volume is 2, that is this solution is diluted, and after whenever the total volume is 2 liters and in the 2 liters 5.8 grams of sodium chloride is dissolved. Okay, so at this concentration or at this dilution, let us calculate the equivalent conductance lambda C, that is which is more than, because on dilution we know that on dilution equivalent conductance increases. So it is for example, let us say it is 2 ohm inverse centimeter square gram equivalent inverse, and if we add one more liter, that is total volume is 3 liters, then equivalent conductance is for example if we say 4, that found to be 4, right, 4 ohm inverse centimeter square gram equivalent inverse, right. And if we add one more liter, that is we are increasing the volume, that is we are diluting the solution, So with on dilution, the equivalent conductances are increases. When total volume is 1 liter, equivalent conductance is 1. If total volume is 2, equivalent conductance is 2. And if total volume is 3, equivalent conductance is 4. And if total volume is 5, that is we are adding 4 liters of water to the initial solution, that is that ions degree of dissociation increases, so equivalent conductance increases. Okay, that comes out to be it comes out to be 6, right. And if we add one more liter, that is 6 liters, that is total volume is 6 liter, the equivalent conductance is remains constant. For example, if you add one more liter, that is total volume is 7 liters, the equivalent conductance remains same, that is 6 upon and a particular dilution, that equivalent conductance increases up to a particular dilution. After that dilution, beyond that dilution, equivalent conductance does not increases. Okay, equivalent conductance increases up to a particular dilution. Beyond that dilution, equivalent conductance does not increases. Okay, so equivalent conductance where the maximum equivalent conductance is maximum at this dilution, that is we are adding 5 liters of water to initial solution. So equivalent conductance remains the same, and after we are adding 7 liters, for example, if we add on 1 more liter, then there is no increase in equivalent conductance. So there is no increase whenever that saturation point is reached, then this equivalent conductance at a particular concentration is known as a infinite dilution, that is represented with equivalent conductance at infinite dilution. Okay, equivalent conductance at infinite dilution, lambda infinite, or more conveniently, or sometimes it is represented with lambda naught, right? So I hope you got the difference between equivalent conductance at any concentration and equivalent conductance at infinite dilution. I hope you all understood that equivalent conductance at any concentration is less than equivalent conductance at infinite dilution. Okay, that is equivalent conductance at infinite dilution is always greater than equivalent conductance at any concentration, right? So lambda alpha is equal to lambda c by lambda infinite. Okay, right. Okay, so equivalent conductance, so conductance ratio alpha is equal to lambda c by lambda infinite, or it is equal to lambda c by lambda naught. Okay, so equivalent conductance at a particular, at any concentration, equivalent conductance at infinite dilution. Okay, the equivalent conductance at any concentration is in relation with the equivalent conductance at infinite dilution by the equation known as a Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation. So equivalent conductance at any concentration is in relation with the equivalent conductance at infinite dilution by the equation called Debye-Huckel-Onsager equation. That equation is actually Debye-Huckel and Onsager, these three scientists formulated the relation between lambda c and lambda infinite by the equation. That equation is lambda c is equal to lambda naught or lambda infinite minus 82.4 by dt power whole power 1 by 2 eta plus 8.24 into 10 power 5 by dt power whole power 3 by 2 into lambda naught into root c. They found a relation between lambda c and lambda naught with this equation. Okay, if you observe this equation, with your naked eye, which is in the form of y is equal to m x plus c. This is in the form of y is equal to mx plus c. Okay, so where m is, this is, x is root c and c is lambda naught. If we plot the graph between y and x, where y is lambda c and x is root c. When we plot the graph between y and x, lambda c versus root c, that gives a straight line. Y is equal to mx plus c gives straight line, but this is a straight line with a negative slope. Straight line with a negative slope that can be represented as that comes out to be like this, right? So that graph is like this. Okay, so negative slope means those one increases and another one decreases. Okay, here lambda c decreases, but whereas root c increases, x increases, y increases, c increases, x increases, y decreases, c increases. So negative slope means y decreases, x increases, right? Okay, so lambda c, that is with increasing the concentration, lambda c, that is equivalent conductance at infinite dilution, decreases. Okay, with increasing the concentration, lambda c decreases. But you read this plot in reverse direction, that is with decreasing the concentration, equivalent conductance increases. Decreasing the concentration means dilution, that is on dilution equivalent conductance increases. On dilution equivalent conductance increases. Similarly, molar conductance also, on dilution molar conductance also increases. Okay, right. Okay, so this is in the form of y is equal to mx plus c, and if we extrapolate this line, straight line up to zero concentration, that gives intercept value, that is lambda naught. Lambda naught is, we know that lambda naught, what is lambda naught? Lambda naught is equivalent conductance of an electrolyte at infinite dilution. Already I told you lambda naught is greater than lambda c. Okay, so because on dilution equivalent conductance increases. Okay, so by extrapolating this straight line up to 0, we can get the intercept value lambda naught, right? And one more thing is very important. From the last class, we know the specific conductance. Specific conductance is the conductance of 1 centimeter cube solution. Enclosed, or specific conductance is the conductance of a electrolyte solution enclosed between two parallel plates or two parallel electrodes separated by a unit distance, right? So that with the specific conductance values, electrolytes are classified into two types. Okay, electrolytes with high specific conductance values, are called as strong electrolytes or strong electrolytes. And electrolytes with low specific conductance values, then that electrolyte is called weak electrolyte. Okay, so basing on the specific conductance values, electrolytes are classified into two types. If the electrolyte with the high specific conductance value, that is called strong electrolyte. Okay, and you know that specific conductance increases with increase in concentration, right? Okay, and electrolyte with low specific conductance values are called as weak electrolytes. Okay, come to this point. Okay, so for strong electrolytes, when we extrapolate this straight line, we get the specific equivalent conductance of electrolyte at infinite dilution. Okay, this is possible only for strong electrolyte. This is possible only for strong electrolytes. Strong electrolytes are the electrolytes where complete dissociation takes place, whereas weak electrolytes complete dissociation does not takes place, partial ionization takes place or partial dissociation takes place. Okay. So, by extrapolating the straight line up to 0 concentration, we can get the lambda naught value for strong electrolytes only. Okay. So, we cannot get the lambda naught value by extrapolating the straight line up to 0 concentration for weak electrolytes. Okay. That can be shown by okay. So, this is the graph of strong electrolyte, okay, and for weak electrolyte that graph does not meet the y axis. That straight line, that graph does not meet the y axis. That is why we could not get the lambda naught value at lambda naught, that is infinite dilution, lambda naught value for weak electrolytes. For strong, this is strong electrolyte and this is weak electrolyte. So, weak electrolyte, the lambda naught value for weak electrolyte cannot be calculated by extrapolating this line or from this Debye-Huckel-Onsager equation. Okay. So, lambda naught of weak electrolytes calculated indirectly by using Kohlrausch law of independent migration of ions. Okay. Kohlrausch law of independent migration of ions. Okay. Okay. So, lambda naught or lambda infinite value, that is equivalent conductance at infinite dilution of weak electrolyte, we cannot get the equivalent conductance at infinite dilution of a weak electrolyte from by extrapolating the curve up to 0 concentration. Okay. So, we can get this value by using Kohlrausch law of independent migration of ions. Before that, let me draw what is it called? Let me conclude a equation, that is equivalent conductance and specific conductance are related by the equation K into 1000 by normality, and equivalent conductance are molar conductance and specific conductance are in relation with one another by the equation this. Okay. If we take the ratio lambda c mu c, that is K into 1000 by normality into m by K into 1000. Okay. These two are cancelled. So, lambda c, that is equivalent conductance at any concentration, molar conductance at any concentration is equal to molarity by normality, and from this molarity, equivalent conductance at any concentration, lambda c is equal to molarity by normality into mu c. So, this is the very important relation which helps in solving the problems, right? Okay. Now, let us go through the Kohlrausch law of independent migration of ions. Kohlrausch law. This law states that equivalent conductance of an electrolyte is equal to algebraic sum of equivalent conductance of cation and anion at infinite dilution, right. So, equivalent conductance of an electrolyte at infinite dilution is equal to algebraic sum of equivalent conductance of cation at infinite dilution plus equivalent conductance of anion at infinite dilution. For example, if we take acetic acid, weak electrolyte COOH, okay. So, this equivalent conductance of acetic acid is equal to equivalent conductance of acetate ion at infinite dilution plus equivalent conductance of H plus ion at infinite dilution, okay. So, but we know that we cannot get the equivalent conductance of an electrolyte at infinite dilution directly, that is by extrapolating the Debye-Huckel-Onsager graph, that is by extrapolating the graph, that is plot between lambda c versus root c, by extrapolating that straight line up to 0, we can get the lambda naught value, but lambda naught of weak electrolytes cannot be obtained by using that graph, right. So, equivalent conductance of electrolyte at infinite dilution, equivalent conductance of weak electrolyte at infinite dilution, we can measure with Kohlrausch law of independent migration of ions, okay. So, that can be from that equivalent conductance of is weak electrolyte acetic acid is we can get the equivalent conductance of acetic acid at infinite dilution by equivalent conductance of sodium acetate CH3COONA at infinite dilution plus equivalent conductance of HCl at infinite dilution minus equivalent conductance of electrolyte NaCl at infinite dilution. If you observe this, CH3CON is a strong electrolyte, HCl is a strong electrolyte, sodium chloride is a strong electrolyte. So, we can get the equivalent conductance of weak electrolyte at infinite dilution from the equivalent conductance of strong electrolytes at infinite dilution, okay. You should keep this point in your mind, okay. So, this is equal to equivalent conductance of CH3COO minus plus lambda infinite Na plus this is equal to algebraic sum lambda infinite of H plus lambda infinite of Cl minus lambda infinite of Na plus minus lambda infinite of Cl minus at infinite dilution. So, now this Na plus cancelled, this Cl minus cancelled. So, what happens lambda CH3COO minus at infinite dilution plus lambda H plus at infinite dilution. So, we can get the this is equal to equivalent conductance of acetic acid at infinite dilution. So, we can get the equivalent conductance of weak electrolyte at infinite dilution by using Kohlrausch law of independent migration of ions, okay. So, this is very important concept and there are several applications for this Kohlrausch law of independent migration of ions. So, by using this Kohlrausch law of independent migration of ions, we can calculate the equivalent conductance of electrolyte at infinite dilution, equivalent conductance of an electrolyte of weak electrolyte. We can calculate we can determine the equivalent conductance at infinite dilution of weak electrolyte. That is the one application of the Kohlrausch law of independent migration of ions. And the second application is we can determine the degree of dissociation. We can determine the degree of dissociation. Okay, alpha, we can determine the degree of dissociation from Kohlrausch law of independent migration of ions, and we can calculate the solubility of sparingly soluble salt. By Kohlrausch law of independent migration, by Kohlrausch law, we can determine the solubility and solubility product of sparingly soluble salt. Okay, sparing solubility and solubility product of a sparingly soluble salt by the applications of Kohlrausch law, right. So, in the after theory classes over, I shall go through the problems based on the Kohlrausch law of independent migration of ions. I hope you all understood this class. Thank you for watching.